Yeah, so by the way, for the assignment, I'll probably put up solutions like today or tomorrow or something, so. I have no idea how long it's gonna take to get marked, but you should be able to like see, you got the right idea. Obviously, there's different ways to solve, more than one way to solve some problems though, so. Yeah, actually, for that question, where there's no point A such that there's two sets containing it and two sets that don't contain it. I'm surprised a lot of people did that by induction. There's a quick way to do it just using Sauer-Schalag theorem or whatever, but I think I looked at a few of the induction ones and they look like they worked, so like, you're probably correct, yeah. Anyway, let's get back to Kruskal-Katona. Just like recalling some definitions here of the compression, the IJ compression, pick out J, put in I if you can, right? Otherwise, don't do anything. Then we have this compression of a family F, which was this kind of weird definition. But the key thing about it is it satisfies these two properties, that the compression of F has the same size as F, the IJ compression. And when you do a compression, the shadow gets, well, it doesn't get bigger. It could get smaller, but it couldn't get bigger. And this is like this thing we were kind of, I was struggling to explain to you at the end of the class last time. I said there was like 6 cases. I thought about it last night. I found a proof with only 5 cases. But so I've updated the course notes, but let's not like dwell on this. It's really not that interesting of a proof. So I'm going to kind of move on and do the interesting part, and then if we have time, we'll come back to this. But let's just assume these two lemmas are true. So compressing can only decrease the shadow. So, so definition, say that family F and choose K is compressed if basically it's as compressed as it can get using this compression operation. So if I apply a compression to F, it just gives me F. So if Cij of F equals F for all I less than J. So you can think of this as somebody gives you a family, you apply compressions to it. So apply the compression C1, 2, C1, 3, like 2, 3, 1, 4, all of these different compressions. And like every time you apply a compression, it stays the same size and the shadow gets possibly smaller. And then at some point, you're going to try doing compressions and like it just can't get compressed anymore. It gets, it gets to sort of a minimal, a most compressed kind of version of itself. And then you stop and you say, okay, at that point it's compressed because applying more compressions doesn't change anything. It's maybe not obvious, but like if you think about it, it's not too hard to see that this, like if you did start with any family that's finite and you apply compressions, this is going to terminate at some point. At some point, you're going to get up kind of as compressed as it's going to get, and so yeah, we can always kind of assume things are compressed. What would be really amazing is if every compressed, like if the only compressed family was the initial segment of colex, like the first M sets in colex. It's actually not true. So maybe we won't verify this, but I'll just write it down. So we take the sets 1, 2, 3, 1, 2, 4, 1, 2, 5 of my family. I believe this is compressed. But it's not the first 3 sets in the colex order. I think that would be the simplest kind of way to just, if this proof worked, like if this, like that would be the simplest approach, right? You just take a family, you compress it. Then if it just equals this first M sets in colex, then you could say, okay, then the shadow is at least the shadow of the first M sets in colex. Unfortunately, that doesn't work. Because this, it could end up with this family, and that's not the first three sets in colex. But everything's not lost, so we can still prove it even with this slight issue. So let's get into the proof. We'll just call it KK, Kruskal-Katona. Let A be at least one, and M be at least one. And let A, so one is at most A1 less than A2. So I've got an increase in sequence A1 up to AK. Such that M is equal to 1 plus sum of AI minus 1 choose I equals 1 to K. And then, let F be a collection with size M. So we want to show that the size of the shadow is at least the sum I equals 1 to K of AI minus 1 choose K minus, sorry, I minus 1. So this comes from like the way we restated Kruskal-Katona last time. So, basically, M is this, and we want to show the shadows of these this. Let's do some kind of induction. We'll do induction on, I think, K plus M. Well, when I think about it, I feel like maybe we only need induction on K. We'll see what happens during the proof. But basically, if I can make K smaller by keeping M fixed, or M smaller keeping K fixed, then we can apply the inductive hypothesis. So it's induction on like K plus M. And the base case, which, so for the base case, I'm just going to consider it when K is 1 and M is anything. Because when K is 1, the shadow is like super simple. Because the shadow of any collection of sets of size 1 is just the set containing the empty set, right? And yeah, so like you can trivially check, that the bound holds. I mean, the point is that I think basically it boils down to the fact that anything choose 0 is 1. So, and the shadow has size 1. So, yeah. You good with that so far? Okay, so now we're doing, so now we're for now on we're assuming K is at least 2. And okay. The point of these lemmas over here is that we can assume F is compressed. Right? Because if there's some compression I could apply, then I would do it and the shadow would just get smaller or stay the same. So we can assume F is compressed. In other words, Cij of F equals F for all I less than J. Because otherwise, we would just keep compressing it and get a better kind of example, and then we would deal with the compressed thing at the end. So in the case K equals 1, you only have one, like A, there's just like A1, there aren't any other AIs. So this is like the sum from 1 to 1 of, so like in the case K equals 1, yeah, I did kind of brush over this. This sum would just be like the sum from 1 to 1 of A1, A1 minus 1, choose 0. But that ends up just being 1, right? We might need to induct on K plus M, but if I can do the case K equals 1, like, because the kind of simplest base case would be like this K plus M equals 2 or something, right? But if I can do the case K equals 1 in general, that in particular handles that case. So, but yeah, I think we're gonna induct on K plus M. We'll see if we need to later on. That's something I didn't really check. But either way, it's gonna work either way. Okay, so we assume it's compressed. So now I'm going to define two kind of subfamilies. So let F sub 1 be the set of all A and F such that 1 is an A, and let F sub 0 be everything else. So it's F minus the things that have 1, or F minus F1. So here's a claim. So I claim that the size of F1 is at least the size of the shadow of F0. So, well, the idea is as follows. Actually, this comes down to being compressed. Because, so I'll write this down formally in a second, but take something in the shadow of F0. That means it's a set in F. So it's like a set, you take a set A in F that doesn't include 1, and you delete something from it. And now imagine I add the number 1 into it. Well, that actually just gives me the compressions like C1 and then whatever thing I deleted. Right? To take something in the shadow, take something that's not, delete something, and then add 1, that's a compression. So every time I do that, that element has to be in here. Otherwise, I could compress, like I could do that compression and the family F would change. Because it would add that set from an F, or that set that wasn't in F1, we could add it to F, and so it would change. So, in other words, so let, let's say A in the shadow F naught. So then there exists something that's not in A, some L. It's not an element of A such that A union L is in F naught. Just by definition of the shadow. And also, if I take, so 1 is not an A. So if I take A union 1, that's equal to the compression C1L of A union L. And since F is compressed, C1 comma L of A union L, it has to be in L. Because if it wasn't, right? We go back to the definition of the compression C1L of F contains the 1L compression of everything in F. If one of those wasn't already in F, then we would get it in here, and we didn't have it before, so the compression would change the set F. So that would mean that it's not compressed. But yeah, if this thing was not in F, well, it is in the compression of F, so then the compression would be not the same as F. So okay, so this gives us the sort of an injection from the shadow of F naught into F1, right? For anything in the shadow of F naught, take this, so take a set A in here and add 1 to it. That's kind of an injective function from this set to this set. So kind of formally, so if we define, let's say psi from the shadow of F naught to F1 by psi of A is A union 1. This is an injective function from the shadow of F naught to 1. Yeah, so when I say this is in F, really it's in F1, right? Because it has 1 in it. So that proves that claim. Right, if I've got an injection, then the codomain has to be bigger, at least as big as the domain, right? Questions about that? Okay. Let's prove another claim now. I think we're done with this stuff, so I can erase this stuff. Okay, so next I want to show that F1 is kind of big. So the kernel of F1 is at least the sum I equals 2 to k, right, 2 up to k, ai minus 2 choose I minus 1. It should not be clear where this comes from. I mean, this is kind of an obscure looking thing. Although maybe, I mean, maybe there is some intuition, maybe, I don't know, I mean, here I've got like a shadow. Like, I've already got the F1 is bigger than this shadow, and like, it applies some kind of induction, like, often we get bounds on shadows that kind of look like sums of binomial coefficients. That's a bit shaky, but let's see how this works. So proof. Well, how big is well, actually, sorry, I'm going to start by bounding F0. Oh, actually, sorry, I'm going to start by assuming not. So it's going to be by contradiction. So assume. And also, I messed this up slightly, that there should be a +1 in this bound. So,
I have a question.
yeah.
So the reason why we can assume that F1 is non-empty is because F is compressed.
Well, we're not even really assuming that, but this is gonna give it to you, right? Like, I mean, I'm actually from the beginning not assuming it's empty at all, but it is gonna be, if we can prove it's bigger than this, then yeah, if this is not, then yeah, it is gonna be not empty. But you could just say it is not empty because it's compressed, because then I could just add 1 to a set and delete something else, and I would, yeah. Okay, so sorry, there should have been a +1 here that I missed before. So assume not. So then. But we're now assuming F1 is small. So smaller than, so it's at most this sum. F naught is the same as taking everything minus F1. Actually, we have an exact formula for the size of F in terms of some binomial coefficients. And if F1 is kind of small, you know, it's smaller, it's at most this sum, we can kind of bound this by. So this is an exact formula for F, for the size of F. It's equal to M, which is 1 plus sum I equals 1 to K, Ki minus 1 choose I. And if we're assuming F1 is at most that sum, so if the +1 isn't there, then yeah. This. Which is equal to 1 plus, so I'm going to put these sums. Well, I'm going to try to put these sums together kind of awkwardly. One of them starts at 1 and one of them starts at 2. So let's split off that extra term. The extra term is just A1 minus 1. It's A1 minus 1, choose 1. And then the sum I equals 2 to K. AI minus 1, choose I. Minus AI minus 1. Choose I minus 1.
The AI minus 2.
Yes. Thank you. So does anyone recognize like something here? I mean, there's this like thing you probably heard about in, I don't know, second year discrete math or something. Does anyone notice like this is like some think of it like, I mean, forget about these things, but think of it like n choose k kind of minus n minus 1 choose k minus 1, right? You know a thing that applies to this? Yeah.
Is it like n choose k equals n minus 1 choose k minus 1 plus n minus 1 choose k?
Yeah. which I think, I mean, at least I call it Pascal's formula or something, or Pascal's identity. Yeah, so this is equal to n minus one choose k plus n minus one choose k minus one. And so like this thing here is just like moving one of those terms to the other side. So then you would be stuck with, you'd be left with this. So yeah, here I've got one plus a1 minus one plus the sum I equals 2 to k of ai minus 2, choose I. So by Pascal's identity, or whatever you want to call it. But to go back to this other plane, so I want to get some kind of a contradiction here. So I showed that F0 is big, kind of, right? It's at least this. And if a collection is big, we can say by induction that the shadow is kind of big. So, and the thing is, if the shadow of F0 is big, well, that's going to translate to F1 being big by this claim. So, so the size of F1 is at least the size of the shadow of F0 by the claim. So the last thing to do is to show that the shadow has at least size at least this, and then we'll be done. We'll be done if the shadow of F0 has size at least sum I equals 2 to k ai minus 2, choose I minus 1 plus 1. This is like almost the right, it's almost the right form to just use induction. Fortunately, there's a slight bit of slight awkwardness for that expression. We need to yeah, we need to be a bit careful. But I guess if this was 1 plus, and then forget this one, and if this was I equals 1 to k, or something like that, like, or yes, anyway, it's almost the right kind of format to apply induction. But by the way, we can apply induction because we know that, actually, we know that F1 is not empty, right? Because it's bigger than the shadow of F0, or by saying, compressions. So we can actually apply induction to F0. So actually, we do kind of need the induction on M in some sense, because F0 is a collection of sets of size k, and we're going to use that F0 is smaller than the whole thing, like it's not all of F. So we can actually apply induction on F0. So we kind of need that k plus M. Okay, so I want to show that. So I want to show this last thing star. Kind of going to break this into a few cases. So let's suppose that A1 is less than, strictly less than A2 minus 1. So then the sequence, I take A1 and then A2 minus 1 all the way to AK minus 1, is increasing. And the size of F1 is at least 1 plus sum I equals 1, or well, it's A1 minus 1, choose 1 there's one plus A1 minus one, choose one plus the sum I equals 2 up to K. AI minus 2, choose I, right? Choose I minus 1. Oh, no, choose I. I'm using, yeah, this. So if you think about what this, it's like, this is my new M. And I applied the inductive hypothesis, so by induction. The shadow of F1 of, oh, this should have been F naught, sorry. The shadow of F naught has size at least. A1 minus 1 choose 0 plus the sum I equals 2 to K AI minus 2 choose I minus 1. So that's how the statement of this Kruskal-Katona thing works. If you have a F naught, if something is bigger than, something like this, you just reduce these things by 1. And then the shadow, and take away the plus 1, and the shadows of these stop. Which would be the same as what we wanted, because that's a 1. Anything choose 0 is 1. So in this case, this star holds. Which then, yeah. In turn, it gives us that F1 is large, and that proves the claim in that one case. Next case. This is going a little bit fast, but I really don't want to come back to this next time. It gets 3 lectures proving the same thing. Like, it gets harder and harder every time to remember what the heck is going on, right? But are there any questions about this thing? The idea is we wanted to apply induction to a slightly different sequence, and we need the sequence to be increasing, and then we can apply induction. The thing is, though, A1, like, we know that the sequence A1, A2 is increasing. A1 could be equal to A2 minus 1. So case 2 is when A1 equals A2 minus 1, and A1 is at least 2. And there's one case after that where A1 is 1. In this case, again, use the bound I proved on F naught. So it's at least 1 plus A1 minus 1 plus sum I equals 2 to K AI minus 2 choose I. And this time I can actually just say, I'm going to throw away something. Just say this is strictly greater than 1 plus A1 minus 2 plus the same sum. So I've just thrown away 1. Which is equal to 1 plus the sum I equals 1 to K AI minus two, choose I. And since the sequence A1 minus one, A2 minus one, up to AK minus one is increasing. Like, I guess in all of these things, when I write A1 minus two, I'm really thinking of it as like A1 minus one minus one. And also A1 is at least one. So this is where I'm using that A1 is at least two. So that A1 minus one is at least one. So in this case, my inductive hypothesis holds again. So by induction, I can bound the shadow of F naught with the same kind of thing, except that I choose I minus one and there's no plus one. So equals one to K. And then I just notice that the first term is one. Right, so I equals one term is like AI minus two, choose zero. Anything choose zero is one, as long as the top part is at least two, or as at least zero, right? So yeah, so this is a game proof star. I feel like this proof is on the verge of being like really beautiful if we didn't have to do these like little cases that like that we have to deal with, but I mean this part, I like this part, but yeah, I don't really. It's kind of annoying to deal with these little cases, but yeah. My last case is that again, A1 is equal to A2 minus one, and this time A1 is one, which means A2 is two. Um, Maybe for the sake of time, because I really want to get to the very last bit of the proof, let's maybe just say for this one, see the notes. But the crucial thing in this one is that is the kind of trivial thing that yeah, it somehow involves the fact that if you have kind of I minus one choose I, that's always zero, and like somehow like most of the first few, like a bunch of terms, well, yeah, you basically have a bunch of zeros and you can kind of think of zeros in different ways. You can kind of mess with the equations a little bit for the quantities and get another increasing sequence that ends up working. So it's not particularly deep, but it works out in a case. Okay, so let's now assume. So we were proving this claim, right? So we can now assume this is true. Okay, so let's finish the proof now. Okay, so. We're going to define a family G, which is a set of all. Sets I get by deleting one from a set in A1, or sorry, F1. Remember, F1 is the sets that have one in them. So note that size of G is exactly the same as the size of F1. It's because yeah, there's a kind of simple bijection between them, right? Like I could take two sets in F1, delete one from them and get the same set, because they all have one in them. So one doesn't really distinguish two sets in there, so. Also. G is a subset of the shadow graph. I mean, it's just all the things you get by deleting one, so yeah. So it's definitely in the shadow. So now I'm going to define a function psi from G union the shadow of G to the shadow of F by, so if I take a set E, which is in the domain psi of B is either B, if B is in G, or we take B union 1 if B is in the shadow of G. So maybe need some justification why this works, right? But so if B is in the shadow of G, I claim B union 1 is in the shadow of F. The reason is, look at the set A. Yeah, to be in the shadow of G, what B has to be is you take a set A in F1, you delete one from it, then you delete something else. But if I put one back into it, I'll get something that was in the shadow of F. Like imagine I delete one and delete something else, and I'll put one back. Well, it's just like if I start with the original set, I deleted the whatever the something else was. So yeah, this is indeed such a function that it goes to the it maps into the shadow of F. And note that psi is injective. It's not too hard to convince yourself of that. So shadow of F, size is at least size of G plus the size of the shadow of G. So what we're going to do is finish off by like remember G has the same size as F1 and we know something about that, right? We know that the size of F1 is this sum of binomial coefficients plus 1, right? So somehow that's useful to bound G and also the shadow of G. And now we're gonna use that to get a bound on the shadow of that. So maybe I'll leave this plain and I'll erase the proof. And then so right. So using this claim and the fact that G has the same size as F1, we can bound G by 1 plus sum of I equals 2 to K, AI minus 2 choose I. So that's the bound on G. And actually by induction, we can bound the shadow of G. Because recall that, G, where does G live? G is a subset of naturals choose K minus one. We got it from taking things in half and deleting one from them. G is a subset of this, where the cardinality of G is at least this sum, which I could re-index this and take it the sum from I equals 1 to K minus 1 of then AI plus 1 or whatever. And this is exactly the form that we need for the Kruskal-Katona theorem. So then we can say that the shadow of G has size at least sum of I equals 2 to K AI minus 2 choose I minus 1. Where would it be? Was there I minus 1 here before? Yeah, there was. I mean, there should be an I minus 1 there, yeah. I'm not sure where it went, but that's a minus 1 and that's a minus 2 here. We use Pascal's identity again. We can put this all together and get 1 plus I equals 2 to K AI minus 2 choose I minus 1 plus AI minus 2 choose I minus 2. And by Pascal, well, and also the fact that anything choose 0 is 1. I can write this as this is A1 minus 1 choose 0 plus the sum I equals 2 to K AI minus 1 choose I minus 1. That's what we wanted. That's the sum I equals 2, or sorry, 1 K AI minus 1 choose I minus 1. Okay, so that's for this. Kind of in some sense miraculous that it works out with all these binomial coefficients, but yeah, it does. Okay, so that's the end of the Kruskal-Katona, and then next time we're gonna do something different.